Hi everyone, I'm Pooja Malik. I have been working at Sedai. I'm a principal engineer at Sedai. I've been working at Sedai for the past 2 years. Before joining Sedai, I was with Salesforce for past 7 years, taking care of their data centers and cloud. So today Vinod will join me. He's also a principal engineer, and before joining Sedai, he was the Kubernetes champ at T-Mobile. So in this session today, we'll cover the internals of what resource configuration is in Kubernetes. We'll also cover the complexities which are associated with the optimization and management, why autonomous and machine learning are the solutions, and what solutions other companies use, and we'll look into in detail of our autonomous solution. So most of you know requests is the minimum resources a container is guaranteed to have, and limits are maximum resources container can consume. Now you can set these requests and limits at CPU, memory, ephemeral storage, and some extended resources like GPU. So the numbers that you see here are the wastage. It's based on a SysTig survey, and these are the wastage numbers that have been reported for CPU and memory. And well, this is like age. They have not never reduced. They have only kept increasing. Um, so before going into the complexity, let's see how this container request and limits work under the hood. So Kubernetes has a process called kubelet, which has to run on each node. Now, this kubelet, the main purpose of this kubelet is to assign requests and limits to the containers. So there is a concept called C groups, and now C groups are the main component which isolates the resources from for the individual containers. Now there are two right now with respect to Linux. There are two versions of C group: C group V1 and V2. So off late with Kubernetes version 125, the C group V2 has become stable, but it has still not been rolled out in all the commercial big clouds. The C group also uses the request and limits to configure something called a Linux CFS, the complexity fair scheduler. So, and there are again two concepts. So, gets translated to request gets translated to shares, CFS shares, and limits gets translated to CFS quota. Now, how these CFS shares works is very interesting. Now, as an example, let's say there is a node which has 2 cores total, and there are 4 containers deployed on it. Two ingress two ingress containers, one machine learning worker, which definitely needs more requests, and an API server. So these are the CPU requests which are assigned to each of these. Now, if you see they get translated to CPU shares, which basically gets multiplied by 1024, which converts it to binary. But again, it's relatable. Then the next number is the node fraction. So in that, out of that 2000 millicores, how many fraction of resources are getting for each node? But the next parameter is way more interesting, which is basically the guaranteed CPU. So that means all the since the total of, if you sum all the requests, the total doesn't correspond to 2000, right? So all the wasted usage, the wasted CPU is still being used. So that's more so about the shares. Now let's talk about the quota, the CPU quota. So the quota, how does that work is it so it doesn't really correspond to the CPU power. It corresponds to how many time slices, how many the CPU node has. So for example, it basically, if you use all of these time slices, then even if you have idle CPU, it'll just wait. Then so this is about CPU. Memory, with respect to the memory distribution, it's not that interesting. It's just, if you reach the limit, you will get out of memory errors. So another thing that is very interesting here is the eviction. So when you are actually setting the request and the limit, you also have to see how many how Kubernetes or kubelet will evict all these pods. So there are there is, and that's those, there are certain guidelines, and one of the most important guideline is the QoS classes. So you have something called guaranteed, where you have the same request and limits, where so that means they'll never be evicted. Then you have the least favorite, which is the best effort, where you don't set a request and a limit, and they will be the first ones to get evicted. Then you have something in the middle, which is bus stable. Again, it will depend on the usage whether to evict it or not. So these are some of the best practices that we recommend to for setting the resources. So again, there are pros and cons. So the pros of setting these is you get a deterministic and well-behaved system. So like in Google, they do set it. It also, if let's say one of your pod is a rogue pod and it's trying to consume a lot of resources, it'll make sure that all the other resources on the node doesn't go down. The cons are the so you are definitely, it's possible that if you set the limit too high, you are wasting resources. Also, as I explained before, there is a chance of extra latency, so you might have CPU throttling if in case you assign it very low, or you might have errors. So the guidance from our side is set the resource and limits based on usage, and also set the CPU limit and request equal same for critical applications, so that they never get evicted. Uh, so so now let's deal with the complexities which exist in managing Kubernetes. So if the if you give a lot of resources, definitely there is a chance of wastage. But if you give too less resources, there are chances of having performance and reliability issues. So the one of the solution that most of the people adopt is doing load testing, right? So if this is a like a real problem that our industry has, that getting your load test as close to production as possible. um, and if you need to get it as close to production as possible, then there's also a lot of cost that you have to incur. So so the uh, takeaway from this slide is it's way accurate, easier, and scalable to decide these configuration optimization configuration based on the observation data that you have in each environment, rather than studying a rather than doing load testing on an application in isolation. So most of the people, the solution for this is auto scaling, and most of the people again understand this. So uh, we have a horizontal pod autoscaler which scales the pod horizontally, adds number of pods. Vertical will increase the size of the pod, and most of the times the horizontal pod or vertical pod autoscaler is also has to have a cluster autoscaler, so that your infrastructure is also increasing. But the auto scaling definitely on in theory looks very good, but again, there are certain disadvantages. You definitely get increased flexibility, you get better resource utilization and performance, but then you still have to configure the autoscaler, right? So there is an increased complexity. It's also possible that you have a resource contention, and there might be difficulty in accurately predicting the demand, because you have a certain max set. So basic foundations of achieving successful auto scaling is that it should be intelligent. Your auto scaling system should be intelligent and enough to sort through all the noise, and it should be able to yield actionable intelligence about the cluster operations and health. You should also have the visibility. It should show you the current visibility, and it should be able to identify the opportunities for improvement. And also it should be autonomous, so it should be able to proactively and continuously right size. So now in this slide also we cover why this thing is so complex that you need machine learning and autonomous in place. So so imagine you have so many um, different inputs, so many different parameters that you have to set. You have to set a CPU request and limit, memory request and limit, storage, replicas. You also have to set a application autoscaler. So you need to know whether your application is a memory intrinsic app or a CPU intrinsic app, and how much on what percentage of memory or CPU or some other factor it will you need to scale up. And you also have to determine the node, the whether what type of node what instance type you have to use. You also have to set up the cluster autoscaler. So back in Salesforce, we spent almost a year, checkists trying to see how to come up with, with load test and everything, trying to come up with the node type. But even then, we were not accurate. So, and all these factors have to take into consideration your load. Uh, that latency should not get affected, the traffic, as well as they should, and you have to do all this for each release. So it becomes a little complex. So with machine learning, it basically elevates the complexities of configuring multiple Kubernetes parameters. With the machine learning predictive models, you can very well relate to reality. Also, uh, it helps in optimizing for business requirements. So let's see what are the different approaches that other companies have taken or which exist in Kubernetes world. So we have tools like APM tools like Datadog and insight tools like Cloudability, which again gives you the observation data, but they will really not give you any recommendation, or they'll not perform autonomously in production. Then we have certain recommendation tools like AWS compute optimizer, which will give you recommendations, but again, we won't execute autonomously. So doing that at scale is very, very hard. Then you have the self-configured HPA and VPA. Again, they are great. Since they act on in production, but again, you need to know what to configure in HPA and VPA, which is harder. And then you also have to make sure that you have a little bit of predictability in order when you're actually configuring HPA and VPA, which HPA VPA doesn't support, and also reinforcement learning. Then you have certain role-based static optimization tools like KubeCost, which again doesn't give you the complete autonomous story. And then you have tools like Sedai, which gives you, so Sedai uses machine learning to come up with intelligent inference from your existing observation data at any scale. It we also use a combination of reinforcement learning, rapid experimentation, and scenario-based analysis to basically optimize your cluster for cost and performance. So next, next Vinod will take over to give you a little bit more details on what our autonomous solution is. Over to you, Vinod.
Okay, so now that you've heard about what the challenges are in optimizing a Kubernetes system, let me talk about how Sedai does it as an autonomous system. So we start with right sizing the workloads. So the reason we start with that is a philosophy is that since the pods in Kubernetes, pods are the smallest units that you can work with. So if we make them the right size in terms of resource usage and the best performance, right? And if we can find the right balance and right size them, then it makes things easier, like in the down the line, like for the next steps. So the way Sedai does it is a combination of looking at past data. So it starts with looking at the past data, at least 2 weeks of data, and then looks at the usage patterns and figures out what size to start with. So uh, we will we will see, you look at the data and then set the requests and limits based on, and also the number of replicas based on the usage to like it's basically an estimation of the best case. And from there, what we do is we do reinforcement learning by changing uh, different parameters and figuring out how it affects the system, how it affects the performance, how it affects the usage. And then after a few cycles, we come up with a good a number that is optimal for a typical workload. So that once we have that, we what we have found out and working with different clients is that it along with cost savings, it also has a performance improvement most of the cases. So in most of the cases, as we have been hearing all day, people size it so that it always performs for all kinds of loads, right? So they oversize things, right? So over allocate resources to a system. So we almost always have a 20 to 30% cost savings along with a performance improvement, which gives us a win-win. So once you have the pods right sized, the next thing we do is right sizing the infrastructure, and that is not done in a day one because we have need time to right size the workloads first. Once once we have the workload right sized, we move on to the right sizing the infrastructure, which is selecting the node types and maybe grouping them according to their workload. So I'll go into detail on this, so I'm not going to spend much time on this right now. I have another slide coming up for that. So once you have like right size the infrastructure, we typically see 15 to 25% savings because we reduce the wastage associated with this. And these two right sizings also will not work unless you have auto scaling at a workload level and also on a cluster level. So I'll also get into detail on that. So because these are right sized only for typical workload. So you do need auto scaling to scale them up or down based on the load demand. Right? And the next thing you can optimize on a cloud is the purchasing cost. This actually gives you the most impact, but it is uh, not easy, or it doesn't happen in day one. It takes a while for Sedai to learn your usage and then suggest what kind of purchasing options you can go for, like uh, reserved instances or savings plans or spot. We have a way of figuring out what percentage or of your workload can go into spot based on the usage patterns, and so that typically gives you around 30 to 60% savings. This is all from our experience, and so then next thing is the auto scaling. So auto scaling, Sedai goes with a hybrid approach where you have reactive scale auto scaling using HPA, and Sedai actually does not do the auto scaling. It leaves auto scaling to HPA, but it does what it does, and what it can do is go and change the SPA parameters like the target utilization, select the right metric, and also it also sets the upper and lower bounds. So that takes care of the reactive scaling. And another thing is the predictive auto scaling, which Sedai actually does by itself. Like it learns the seasonality of the load of your load, and predictive, like proactively scales it right before the load is going to increase. So I'll go into another slide where it shows an example. The last part is actually, this is the unique part where only autonomous systems can do this, is continuously optimizing. right? And this is done using what we call release intelligence, where Sedai monitors each release, and it looks for different parameters and see if each release, what happened in each release, did the performance increase or decrease, or does the cost increase, and it gives you a detailed report. And also it uses this data for future optimizations, and the optimizations we talked about earlier is all done continuously for every release, all the time. So if it finds a release and it does not see much difference, it might not attempt an optimization. But if it does see uh, a change in, let's say, performance, then it becomes a good candidate for the next optimization. Next slide, please. So this is to go into a little bit more detail into node optimization, how we do node optimization. So the node optimization, the first thing is to select the node type that you're going to use in your cluster. So most of the people, what we have seen is they select a general purpose node and they just stick with it. So most of the time, workloads are either memory intensive or CPU intensive, and we have seen both. And there are clusters with a shift to one side also. So one thing we can do is, like, basically selecting the node type. It involves looking at CPU, memory, even network, because some of the applications are completely network bound. And what we have seen is people go for larger node types because it gives them better performance. But the underlying reason might be that the bigger instances have better network, not because it has better CPU or memory. So Sedai can identify all this and select a network, a node type based on all these parameters. And of course, GPU, you definitely need a GPU based system, a node type if you have a GPU workload. And also the latest types of nodes, like for example, AWS releases new node types every year. So every time a new generation comes out, it has a better performance for practically the same cost. So we also consider that. And also the Intel versus AMD is basically Intel and AMD, like Intel has better performance most of the node types in terms of AWS. So we have found around 10% improvement in cost when the systems, the applications, the workloads running are not CPU bound, by moving them to an AMD based machine. So another thing we optimize for is if the cluster has a large number of daemon sets, it is actually cheaper to run everything on less number of nodes rather than larger number of nodes. So, and also there are multiple other parameters we look at, which is not listed here. Like if you have a monitoring provider, let's say Datadog or SignalFX, which where the billing is based on the number of nodes, we can also optimize for that. So that is one type of optimization here, and the next type is the node grouping, which is not applicable for a smaller cluster, but for larger clusters, it is very economical if you group the nodes or the workloads into different node groups or node pools, where let's say we move all the CPU intensive workloads into one node group and select a CPU intensive node type for that node group. Right? So that actually reduces a lot of wastage, which you cannot achieve without this grouping. Next slide, please. Okay, so this is an example of combining both workload and a node optimization. So if you look at the application, this was actually Sedai found that this application was memory bound and increased the memory by 25%. And by increasing the memory 25%, we saw a latency improvement of 30%. So which suggests it might have been heavily uh, garbage collected or something, right? It was, so the usage was pretty high, and there was a lot of garbage collection going on. So it benefited from increasing this memory, just 25% of memory, and it gave you a 30% 33% improvement in latency. The next step, what we did is the reinforcement learning found that it does not need that much CPU. So Sedai always it does increases first, and decreases are done later on once it gets comfortable and it does the reinforcement learning. So the reinforcement learning in this case found out that the CPU needed is much lower than what is being requested. So it reduced that CPU request and limit, and then it we moved on to the node type, and since it's a memory intensive application, we selected a memory node which happened to be a AMD node also, as well, and that and also because these R6 AX large has double the memory of an M5 X large, uh, we were able to run this workload on half the number of nodes. And so all in all, the cost reduction amounted to around 48%. So this is an example where it's a win-win. You reduce the cost as well as increase the latency, which is pretty hard to come by in Kubernetes workloads. Next slide, please. So here we see an example of reactive autoscaling, and how just with reactive autoscaling you cannot have a very responsive application running. So here you can see that the blue line is the load, and you can see it increasing at around, I don't think you will see the time here, but it's around 9 o'clock. And it's probably by the users logging in or something, the load is increasing. And this is a seasonal load, but and the load autoscaler is tuned to scale up when the loading the probably the CPU or some kind of latency or something increases, right? In this case, it does scale up, but what happens is the load is actually, it keeps on increasing, right? And the increases that the load the autoscaler is doing is not catching up. It is not enough to handle the load, and it does finally catch up, and it does bring the latency down. But there is a point in time, around, in this case around half an hour, where the half an hour or more actually, where the latency is really high. It is exceedingly high, and there could have been outages, partial outages as well. So this is just wanted to show this so that you understand the how reactive autoscaler by itself will not work in most cases. Next slide, please. So in this hybrid approach, we see an example here where Sedai is actually looking at the patterns, and it is showing a 5 days worth of traffic in the first screenshot here. It's you can see that there's a day-night variation in load, and it's pretty consistent, slowly tapering off. And Sedai is able to learn seasonality on a daily basis, on a weekly basis as well. So it does identify that the last days of the week is actually a little lower, and you can see that the predicted load and the actual load is actually very close in the second screenshot. And so in the third and fourth screen, actually the third screen, the last screenshot, you can see that the predicted workload and the auto-scaling plan is actually it's working very close together. With the auto-scaling is actually happening way before the load has time to scale up, load increases. So the auto-scaling, the pods will have time to catch up and work without a latency increase, like a significant latency increase. So that is why Sedai suggests and implements a hybrid approach using predictive and reactive scaling. So the reactive scaling is not reactive scaling is done by HPA again, and the predictive scaling is done by Sedai ahead of time. Next slide, please. So this summarizes the technical approach, as in how Sedai operates autonomously on a Kubernetes system. So, going into detail on all these parts, we wouldn't have time for that. So I'll go into the important ones where so I would say the most important part is the metrics part, where you have monitoring data coming from multiple sources here, and those all these sources, it is piped into Sedai using our own metrics exporter, which can handle pretty much any modern monitoring provider, and these are converted into curated metrics in a form that Sedai can understand. And on top of that, you can see that cloud topology is being derived from Kubernetes APIs, and these two combined gives Sedai an idea of what the workloads look like and how they behave. And these are collected periodically, and um, that is what drives Sedai's decisions, or what gives the information to drive Sedai. And we have AI engines working behind the scenes, and which we explained earlier, right? For anomaly, there's anomaly detection, predictive scaling, which anomaly detection basically just forecasts a coming problem, like based on just patterns, it can identify patterns and predict if an issue is going to happen. For example, if there's a out of memory going to happen, you see a steady increase in memory usage, and the pattern shows that it's going to cross the limit, so they can make corrective actions there. And seasonality, we already saw what seasonality prediction can do with predictive scaling. And so
the first question was, is it recommended to use HPA and VPA together? Any risks? What's the recommendation?
So it's not recommended to use HP and VPA together, just because the resources, like, it's very much possible that you configure your HP on CPU and memory on and VPA on memory, and your your memory is not being used, CPU is being used. CPU will say to increase, VPA memory will say to decrease. So because of all this contradiction, it's not recommended to use VPA and HPA together. Most of the companies, like in production, I have not seen anybody use VPA in the autonomous mode. Everybody uses it in the recommend mode along with HPA, and they use the recommendation from VPA into their configuration. But doing it at scale is so hard. That's why people avoid it.
Thank you. Second question and final question. Kubernetes has significant automation and HPA. How would you summarize what the autonomous approach adds on top of that?
So it does have HPA, VPA, but you have to configure it, right? You have to know whether your application is CPU intrinsic, memory intrinsic, or there is any other factor. So that most of the people don't know their application, and it differs by each environment. It's very much possible in one environment it's CPU, in another environment it's something else. So that is something that we provide. We provide it based on your observation data instead of you looking at an application in isolation. So
let me add on to that a little bit. Since Kubernetes actually has a large set of automation, and it takes care of a lot for you, right? Like in terms of health checks, it can restart a pod. So Sedai tries not to step into that area where Kubernetes is good at, like HPA and monitoring the pods and taking care of the health. It leaves all that to Kubernetes, which does that pretty well. And Kubernetes is also, Sedai is also hands off on HPA, as I mentioned earlier. It only tunes the parameters for HPA. That makes sense.
All right. Thanks very much.